My name is Keita Teranishi from Sandia National Laboratories in California. And this talk is not about like showing achievement of using KLEE, but I just came here to so that I can get comments and advices of our new project, which is trying to make an automatic test synthesis for performance portable programs. And this project is funded by Department of Energy Office of Science Oscar X-SAC project. And it is also joined with several people from Sandia and also Georgia Tech. So before talking about our project, I just want to give you just an introduction and also motivation of our project. So today in DOE US DOE are trying to deploy several large-scale, extreme-scale computing systems, and we particularly call it exascale computing systems. And currently, there are several computing systems already deployed. And also, I'm just trying to talk about one of the systems. It is not a US machine. It is deployed by RIKEN Japan, which is achieving #2 in top 500 supercomputer list, which is RIKEN. But you can actually see in multiple supercomputing systems, they have different architecture, node architecture. Also, they are using different programming systems and runtime in order to run large-scale parallel scientific applications. And now we are having a couple of new systems, which is NASC Perlmutter, which is based on AMD CPU and NVIDIA GPUs. And also recently, Oak Ridge National Laboratory got Frontier systems, which is fastest or largest supercomputing systems in the world, achieving 1 exaflops with a high performance impact benchmark. It is based on AMD CPU and the GPU. And now next year, I think we are having a couple of other supercomputing systems. One is Argonne National Laboratory Aurora systems, which is based on Intel Xeon and also Intel GPUs, and using DPC++, which is a variant of Psycho programming runtime. And also Lawrence Livermore National Laboratory is going to have El Capitan, which is based on AMD CPU, AMD GPU, and of course the runtime system is going to be HIP and also OR OpenMP version 5. So the question is how to deal with this difference, diversity of CPUs and also diversity of even the GPUs, and we also have to deal with heterogeneity of programming. And also on top of that, diversity of programming systems. That is a total mess. So in order to resolve this problem, there are a couple of projects going on in the US DOE. And one of the projects is called COCOS, which is an ecosystem of performance portable programming environment. And COCOS is a C++, modern C++ library APIs, and that is actually hiding the details or idiosyncrasy of individual programming runtime systems, including OpenMP, CUDA, HIP, and also DPC++. And of course, it also covers a couple of kind of legacy parallel programming models, such as PSLED. And the most important thing for COCOS ecosystem is it provides a good abstraction of program execution, parallel execution, and also data representation. And on top of that, it also provides a suite of tools, performance tools, and also some documentation and tutorial, or also boot camps, or some other type of user support. And also, they are also doing some research on distributed parallel computing, and also providing some library kernels for linear algebra and graph operations. And I just want to briefly give you a very simple example of COCOS performance portable programming model. And I'm just putting two code snippet. The one in above is just a regular sequential programming, and it is just running with just for loop. And the one in the below is COCOS, using COCOS and also using COCOS parallel execution abstraction in order to run that loop using parallel, in parallelizing this loop. And also, so you can actually see the data representation is no longer array or vector or standard vector in C++, but it is using view, which provides some template parameters and to abstract the data deployment or data location and also data types of array-like data structure. And the parallel 4 indicates that part of the computation which is represented by either lambda or functor is actually executed in parallel. And as I said, it is modern C++ based on C++ 17 and providing execution abstraction for execution patterns and also data objects. And the nice thing of Cocos programming model is you can actually write one single source to cover multiple architectures. And of course, maybe you may have to deal with changing some template parameters, but if you provide default execution space for view and default execution space for, default memory space for view and default execution space for parallel 4, basically Cocos automatically chooses the target runtime and target devices during compile and build time. And as I already mentioned, so major concept is abstraction of execution space and memory space. And if user wants to actually choose their own execution or memory spaces, there are several options like CDR, OpenMP, and CUDA and heap, and so on. And today, Cocos actually accommodates several applications, several large-scale applications. One is NARU, which is a simulation of a wind turbine developed by NREL and Sandia. And another one is the Sandia lamps, which is a very famous molecular dynamics application. And also University of Utah, UInter, which is a big combustion core. And also Oak Ridge National Laboratory is developing large AD simulations called RAP using Cocos so that it can run all these type of machines. So Cocos provides good abstraction for program execution and also data representation, but it is not a free lunch. And because actually this portable abstraction ironically allows non-portable implementation. Think about using, because Cocos provides some flexibility of tweaking template parameters and also other performance-related parameters for parallel program execution. If you choose wrong parameter, then you mess up a program. Typically the bugs or manifest on specific platforms because typically the user start programming on regular CPU-based machine and making sure it is running on their machine, CPU machine. And then once code is ported to other platforms such as GPUs or maybe new architecture, then the program crashes or getting incorrect results or getting poor performance. So actually the, code diagram on the right-hand side indicates 3 different types of Cocos programs. The one on the top only runs on CPU. And the second one runs both CPU and GPUs, but it is not, performance is not tuned. And the last one is running on both in CPU and GPU, and the performance is well tuned. But in order to reach that point, of course, users, developers have to go through all the development and debugging and understanding the details of underlying architecture. Actually, it is not what Cocos is intended for, but still users have to do that type of code development in order to achieve good performance. So this is not good news. That's why we need some tools to guarantee the correctness of Cocos programs. So in order to solve, so our approach is Cocos. It is basically KLEE for Cocos in order to achieve automatic test code generation. So we are trying to leverage KLEE, and we are trying to also establish a portable formal specification of Cocos API and for model checking. And also it treats all Cocos method calls as uninterpreted function calls, so that we don't have to go symbolic analysis, not into the details of LLVM, IRs, because we don't care memory. We don't care like each single of instructions, because we really care portability, not architecture specific, not architecture specific or not CPU oriented instructions. We really care how COCOS is called, how COCOS data structure is accessed. So this is why we really want to capture the way in the way COCOS, all the COCOS method is called. So, and in order to do this again, so we need to track symbolic state of COCOS data representation. So that means we have to create internal data representation, internal like bitmap or data representation inside KLEE. And we also try to automatically detect the suspicious portion of the code. So lots of talks are talking about like eliminating false negatives or trying to make 100% coverage. But for our project, still it creates a great benefit to the users if this tool can actually detect some suspicious part of the source code. Because then that actually draws attention to the users, then maybe they can try to understand what is going on before running their program on big machines. And so our approach, so in order to actually allow that analysis with COCOS and KLEE, so we actually start with understanding how COCOS is compiled. And COCOS is a templated C++ library. So the previous problem is when it is compiled into bit code. So the number of basically symbol is gigantic because it is templated C++. And so the each symbol for each of the COCOS method code is just so large and it is hard to manage. So our approach is using Clang ASD to transform COCOS program to C-like COCOS proxy libraries. And that means we are creating also special COCOS proxy library, and also we create the rules to transform COCOS programs to C-like function calls. And this actually approach allows us to reduce the size of the symbol tables, and so that we can manage all tracking all COCOS calls or a major part of the COCOS calls. So using this approach, so we are basically converting COCOS application into COCOS proxy calls, and then bytecode, basically becomes just, bytecode looks like most simpler, meaning all COCOS symbols is kind of short enough so that we can actually handle. Then after that, we actually pass into KLEE, and we also provide we also put some COCOS proxy module, and that actually creates some models and approximation of COCOS behavior. And also we use COCOS proxy library, which is very similar to how KLEE handles C or UC libs, and also recent standard C++ libraries. And also I want to also emphasize, we are not performing any floating point operations at this moment. As I said, we really care how we call COCOS, how we handle, we call COCOS. We really care if the user is understanding the operational semantics of COCOS rather than the outcome of the computation. Because outcome of computation goes after we are checking, we are making sure the correctness of the usage. And so I just want to give a little bit of details about what we are doing right now with COCOS proxy library and we integrated with KLEE. So we just trying to make COCOS view as a symbolic, as I mentioned, and basically we intercept all the functions like a COCOS proxy created, which is basically data allocation of COCOS view, and we also trying to create a symbolic path for the metadata object. To detect anomaly or in synchronization or any type of potential race condition or other misusage of index for COCOS views. And we also maintain COCOS view metadata to track mirror. Mirror means, for heterogeneous architecture such as GPU and CPU are putting into together. Actually, the data on GPU is mirrored from the data on CPU. It is called the COCOS mirror. So we also track all the mirror object or references to original COCOS view, and so that we can understand the state of the duplication. And we also try to create abstraction for the COCOS's computational resource representation, league, team, and threads, which is basically indicating the group of threads, league, group, devices, and group of threads, which is equivalent to thread block for NVIDIA architecture and thread, and so that it can serve some metadata for tracking the access to individual COCOS views. And again, we are using COCOS proxy library to do some heavy lifting so that we can do some operations outside KLEE. And we also trying to exploit that idea of COCOS mirror and metadata for COCOS mirroring to detect the heterogeneous data inconsistency. Because, so as I said, COCOS parallel 4 allows basically parallel program execution. But if you choose, depending, you can actually switch the template parameters to indicate where that is executed. And if user is making actually executing parallel 4 in CPU and GPU without any synchronization, it creates data inconsistency. And we also making sure the state of data consistency between them. And I just want to show one case. It is just trying to detecting the potential race condition. It is not exactly race condition because it really depends on number of threads used for parallel 4. But this is, but at least we can understand it is just indicating potential race condition. And our COCOS proxy library translates original COCOS program into this like C-like programming so that we can do some analysis. And it is also another case for potential race condition. Basically, it is using, we are using unaffine basically array access, unaffine access to COCOS view because thread, this my index thread I is undetermined at this moment. And in that case, we can say the way we access COCOS view is not undefined. That means we are having potential race condition. And we are also we are using some COCOS metadata representation inside KLEE, and so that we can actually we can detect a very simple COCOS view mistake, COCOS mistake with COCOS view. So this is one mistake for copying COCOS view A, COCOS view B, because the size is different, 110, and we can also take care of that type of mistakes. And I just want to also so I just last before any closing the talk, we are also working on COCOS formal specification called mini COCOS. So we are trying to create a subset, trying to get a formal specification of the subset of COCOS, and that we are currently trying to understand what that means for improving or help in reducing the search space for KLEE. But at least what we have found is our formal specification already found bugs in the original COCOS implementation, just a pencil and paper exercise. We are still working on that to cover all the specifications, but I'm hoping we can actually leverage this formal specification to improve COCOS implementation. And I think our future and ongoing work is evaluation with a suite of COCOS mistake examples. We are actually having more than 10 program sources that represent the typical COCOS programming mistakes. And we are also having application trying to apply partial symbolic analysis because most of large-scale programming application is using only called COCOS, or maybe less than 10% of the source code of large-scale application is just using COCOS. So we don't have to basically analyze the entire source code. We just want to analyze only small part of the source code. So I think partial symbolic analysis may help in order to detect potential bugs. And again, we are also trying to evaluate, trying to leverage existing COCOS mini applications, mini MD, mini FE, mini IRO, so that we can show that how we can understand the performance of COCOS with more realistic programming application source. So this is the end of the talk, and thank you for listening.